Okay, I think chapter 10. Of course, this is our Logic 500, all these data files you have to keep up with. What we got to learn though is here. I haven't gave you all this yet. I need to do that. So these are the number systems that we deal with. Blue, of course, that's a single bit, right? I understand that. Then we have byte words, double words. Then we have unsigned integers, which gives us extremely large numbers. Then we have unsigned small integers. And then we have unsigned double integers. Then we get into our signed numbers, which is primarily what we deal with. We have a small integer, which is 8 bits. We have an integer, which is 16 bits. And then we have a double integer, which is 32 bits. Of course, we know so if we've got 16 bits, then we get 2 to the 14th combinations, right? And you'll understand that. Yes or no? Huh? And then we take off one of our positive numbers because of 0. 0 occupies one of our slots. So, and then we have real numbers. We have real numbers are signed numbers, by the way. These are 32 bits primarily what we use. Now, the way we get more combinations with this is this uses scientific notation. So, the most significant bit, so bit 31 would be the signed bit, and then you have the base, and then you have what you raise it to. It's a certain bit that it works on. And then characters, these are ASCII characters that we can send to different devices like HMI panels and stuff like that. So programs, we'll look at adding, we'll look at subtracting, multiplying, dividing. We'll look at some additional instructions that's available. This PLC supports all your trig functions. So your sines, your cosines, your tangents, and then of course the inverse. So these are some terms we already looked at. So PLC is a program, a digital computer used for automated and typically industrial electromechanical processes such as control machinery on the factory assembly line, amusement rides and light fixtures, and a bunch of other stuff, right? An instruction, we talked about this, it's a command given to a computer by a computer program. Of course, a program is a group of instructions organized in such a way to make the computer perform a specific task. And a programmer is a individual who writes computer programs. So that's basically what y'all are today. Y'all are computer programmers. Operand, we need to make sure we understand this. This is the part of an instruction. This is the number that the instruction is operating on and manipulating. So if I was to add 3 plus 2 plus 5, then 3, 2, and 5 would all be operand. And then the plus would be the instruction that tells it what to do, right? Does that make sense? Real numbers, this is what RS-Logic 500 calls floating point numbers. That's why I put that in parentheses. If you get to a plant that's still using RS-Logic 500, most new PLC programmers calls them real numbers. So floating point numbers means the number has the ability to move within the number. That's all that means. A signed number that has a fractional component and uses scientific notation. Absolute value, the weight of a real number regardless of the sign. Everybody okay there? Okay, guys. So an array, we've already talked about that. That's a group of operands stored and stated in memory addresses. They're very easy to access. Scientific notation is a method of representing very large and small numbers in terms of a decimal number multiplied by power. Of course, we hopefully know what individual notation is, right? A constant relative to programming, a number that cannot be changed without changing the program. A variable relative to program, this is a number that we can change without changing the program. This is the way we specify bases. So we won't use this much now, but the next instruction the next I think topic is about doing logic bitwise, what we call bitwise logic. So this is the way we specify numbers. So in the O500, what you would do is you'd enter a bunch of ones and zeros, and by default, the application assumes that your numbers are decimal. Y'all understand that, right? Displays everything in decimal, which most of the time is okay. But when we get into doing logic like ands and ors and nots, or trying to strip off bits or add bits, then we're going to have to do this either in binary or another base that we understand. I mean that makes it easier for us to do this type of stuff. So back in RS Logic, if you entered a bunch of ones and zeros, if you entered a bunch of zeros, it would just take it as decimal unless you entered the number with a what? A small case b, right? Okay. And then octal, if we entered an octal number, which looks very similar to decimal, it would take for granted if you wanted to tell the computer that it was actually an octal number, we'd enter an O in a lowercase. If it was a hexadecimal number, it would end up with a lowercase h. With RS Logic 500, they use the IEC standard, international standard, and the way we get separate, specify binary, we'll put a 2 and then a hashtag, and then we enter the binary number. For octal, we'd enter 8 and then a hashtag, and then we'll enter the binary number. And if we're going to base 16, we'd enter a hashtag, and then we'd enter the binary number. In fact, this is what they're showing you up here in this chart, where they're actually giving you the range in hexadecimal. So right here, this chart. So 16 hashtags, so that's a hexadecimal number. That's not a binary number, that's hexadecimal. And we can specify that. Normally we do it when we set up logic like ands and ors. So you're going to AND two numbers together, and you say 932, you're going to add that with 563. That don't make any sense, right? You understand? Unless they're in what? In binary. Then you get an answer. The answer is going to be in a decimal, which doesn't make any sense to you. So we'll really start using these when we get into logic, or when we start doing what we call math. I must be going backwards. Oh, I did. I went backwards. So 2's complement. Two's complement, the method of use to represent signed numbers in all computers, even your calculators. The most significant bit determines the sign. So a 1 means it's negative and a 0 means it's positive. So since this, and of course I left off in our real numbers, and real numbers use this sign, use this system. So 2's complements allow subtraction to be formed with addition. We have three methods to take the 2's complement of numbers. We can borrow a 1, and then we can subtract it from 0. So that means I would come over here, and if I had this binary number right here, and let's set up the drum. So right now it would be a positive, and I wanted it to be a negative, and what I would do is I would subtract it from 0. So you'll see this in text. When it says negate, it says it's going to subtract it from 0. And what I would do is I would come over here, and I would have to borrow 1, right? So I'd generate a borrow, and this would be 2. I borrow from that, make it a 1. This will be a 2. I'd borrow from that, make this a 1. This will be 2, 2, 2, 2, 2, 2. And then I subtract, this would be 1, 1, 0, 1, and I add 0, 1, 0, 1, and that would be negative. Now the beauty of it, if you looked at it at base 10, so let's say I wanted to subtract 53, and I wanted to subtract 29 from it. Well, the problem is I don't have a minus sign. So we'll do it with something called 9's complement. So what I want to do is I want to make that number negative. So let's go ahead and do the math. So what would 53 minus 29 be? If this works out to be right. 24. Everybody okay? All right, so what I'm going to do is I'm going to subtract 29 from 0, and I'm going to generate a borrow. So this will be a 9, and then this will be a 10. What would that give me? Huh? 71. So what I'm going to do is I'm going to take 53, and I'm going to add 71 to it, and I'm going to drop the carry. What do you come up with? Adding. I come up with 124. Drop the 1. You get exactly the same answer. So you drop the carry. This is what 2's complement just did. So what we can do, believe it or not, microprocessors cannot subtract. What they do is they take the 2's complement of the bottom number and they add them together and ignore the carry. So basically, when we tell it to subtract, the microprocessor can't do that. Another way we can do it, so when you look at the negate, when you look at the negate command, when we get into that, it says it subtracts it from 0 and adds. That's what it says. So isn't that cool? So what I can do, if I take the 10's complement of every number, then I don't have to subtract anymore. I'll always do what? Add and drop the carry. Another way we can do it is this is how it got the name. We can take what they call the 1's complement, which means invert everything, and then add 1 to that. So y'all not going to have to do this, by the way, so don't get scared. It does it for us, but we're just demonstrating what we could do. So I've got this binary number right here. And then I'm going to take the 1's complement of it. So I come up here and do this. So 1's complement means invert everything. And then I would add 1. And that would be the 2's complement right there. Another thing, a student taught me this, by the way. He must have found it somewhere. It wasn't. Is you can take a big old number and you invert everything after the first one from the left. So I could come over here. So that's the negative. I could come over here and say, I could start off with this number right here. So I could say 0, 1, 0, 1, 0, 1, 1, 0, and invert everything after the first one. So I'd go 0, 1, 0, 1, 0, 1, 0, 1. And yeah, from the left, yeah, from the right. You just said after the first one. So if I had a number like this, then I would go 0, 0, 0, 1, 1, 1, 1. Of course, I got to have another 0 right there. 0, 1. And that's the easiest way for us to do it. But what the computer does, it just subtracts it from 0. Pretty neat, right? Well, no, I'm not. It takes the 1 complement and then adds 1. So these are the instructions we'll look at. So we'll look at, so we'll see that. They'll say it negate. When we look at the negate instruction, what do you think the negate instruction is going to do? Well, if we negate a number, let's say we negate a positive number, it will become negative. If we negate a negative number, it will become positive. It changes the sign. So negate changes the sign of the number. Square root. This determines the remainder. I haven't seen this before. So if we have a division that has a fractional remainder, this is supposed to give us the whole number we want. Compute. This allows us to enter an equation So we can enter an equation into a box and it'll do that equation, which is really neat. Add, subtract, multiply, divide. Square, negate, what they did. Absolute value. It'll convert any number. It'll just drop the sign, right? Everybody okay on these? I hope so, because we talked this quite a lot. In fact, I need to add that, those other ones. We're not going to look at this. Addressing mode is the way we address the operand. Immediate, in this computer, we have immediate addressing. That means the actual constant operand is specified within the instructions. Direct, a tag name is used to specify the location of the operand. So this would be an example of a tag name. We have indirect, which we're not going to use, but the tag name points to an address that contains the operand's tag address. And what you would do is you would put the tag address inside bracket. And then there might be more. These are the only ones I see. These are the addressing modes supported by RSLogic 500, which we were taught in this class. Oh, by the way, the RSLogic 500 dedicates a lot of memory to different things that we can address. And one of the things that we probably need to get to is when things happen. So this register right here, S:0/0, so the S, it's actually the S2 register, but we don't have to specify 2 because it understands that. This holds what we call a carry flag. An S0/1 holds an overflow flag, which means we did what? Whenever we exceeded the range of our signed numbers, right? S0-2/2 is a 0 flag, which tells us it's a flag. Tells us that the results of the math came up to be 0. S0/3 gives you the sign bit. S0/14 gives you the math. I don't know what that would mean. And I'll go back and see. This is the sign bit or flag bit that's available with RSLogic 500. We have a first scan flag. We'll use this, by the way, if you take PLC3. So anything, and this would be an input instruction, anything that you want to execute the first time a program runs, you would use this thing right here. So what it does on the RSLogic, on the Festo line, is anytime you hit reset, what it does, it runs this anytime you start the PLC up, it runs out and clears out all your outputs, just clears out all the outputs and gets it started from 0, right? And then lets the program set. After that, we have SN, that's the negative flag, SZ, that's the 0 flag. S:(V) is the overflow flag, S:(C) is the carry flag, and that's the flags available here. So here's the basic add instruction. So the add instruction, we run 2, 2. We have source A, source B, and then we have the destination. So when we look at this, this can be immediate, or it can be tag. This can be immediate, or it can be a tag, and this right here has to be a tag. And both of them can't be immediate. If I had an instruction that added 5 plus 5, and that's all it ever did, then I would just use 10, right? You understand that? So they both can be tags, or one of them can be a immediate address. It can be operator. The destination has to be a tag. Are we okay? This makes sense? Questions? So source A, source B, and adding, it makes no difference who you use on the top or the bottom. No matter if you add 5 plus 3, it's 8. If you add 3 plus 5, it's 8. It doesn't really make any difference. It's going to make a difference when you get into subtract and divide and those type of instructions, right? You understand? So this is the top number. What do they call that on addition? What do they call the top one? The sum is down here. So this is added to this, and this is the decimal. So it's just like we write it in math, right? Does that make sense? So B is added to A, but like I said, in addition, it don't make any difference which how you arrange the numbers, but it will definitely make a difference when you subtract, because 5 minus 3 is a big difference than 3 minus 5, right? You understand? So we were very, very cognizant of that. And of course, these are dense, so these are 32-bit signed numbers. So we got up to what, 1.2 billion answers we could have without overflow. Operands, two operations, source A and source B, hold the source data, contents of source B is subtracted for source A. Both A and B can use direct addresses. One can use immediate, the other has to use a tag. Both cannot be immediate addresses. Result is placed in the destination, which is going to be a base tag, right? Because it's not going to. So this is an example. So this is going to whatever's at this address, going to be added to whatever's this address. Is everybody okay? That's an example. Yes, no? Okay. So what we'll I thought I had it open yet. One of the programs that you'll use. So we're using a move. We're using a move, and then we're moving into. So here we're using immediate, and then of course here we're using tag, right? So right now we've got 1500 in here, so we'll go ahead and download it if it lets me. So my first one, so the first one's just going to, so here's my ad. So it's going to say, what's here? It's immediate. And it's going to pull on that tag address up there. So I'm going to come over here and hit switch 0. We're okay? Make sense? Yes, no? Everybody okay? Steven, you okay? And of course, we can look down the rest of them. Subtract. So here we're taking 100 and subtract So this is the constant. So 1500 minus 100. First, I should have changed that over and made it minus. Subtract, multiply, divide. Divide, we're going to have to use real numbers. And why is that? Yeah, there's a high probability we're going to end up with a fraction in division. We don't really watch our numbers. So what we would do is answer 3. Then I could come up here and change this right here. So I come over, click right here, and change this to a what? Yeah. Change this to a real number. Are we okay? Does that make sense? And of course, here's my number here, which is used by everybody. I could change this to a real number too, right? Are we okay? Make sense? Yes, no. So see what I did? Came into my tags, and then I come up here and found the number, and then I could change that. But down here, I changed answer 3, which I hope that's division. I changed the answer to a real. Yeah. Huh? Yeah, division's got to be real. So my answer 3 is my divide. So I changed my answer to a real number. So that way I wouldn't worry about that. But if I wanted to use fractions, then we would have to use tag addressing. And we would have to go here. So here's number. So if I wanted to use fractions, then I would have to assign tags on all 3 of them, right? Understand? And then change them all to real numbers. If I wanted to use, so that way we could enter fractions. If we never want to enter fractions, if we don't deal with fractions though, we don't have to do that, right? In fact, I think, let me look at this. So by default, it's a dent, right? So edit tags, this number. Okay, let's see if we can change it to a U. Yep. So what I just did, if I know I'm never going to deal with negative numbers, then we can change it to an unsigned dent. Now, unsigned dent, then we get 2 to the 32nd combination. Y'all understand that? It should be over 4 billion answers. So, yeah, so these are, by default, it's going to choose a what? It's going to choose a dent, right? But you can go into if you assign in a tag, you can go in and do what? You can change the resolution. So if you don't need signed numbers, then you can take that feature away. And if we take that feature away, what that means is we get a lot more combinations before we get an overflow, right? That makes sense? Of course, we can't have signed numbers. All our numbers would have to be positive. So all of them are basically the same as far as what they did. No, it says that's not supported. So no, we can't make it. We can't make it a dent. So it's got to be signed numbers. So our math has got to be signed numbers. So I learned something. So that's pretty much what add, subtract, multiply, and divide. It's just you make sure on your divide that your answer is at least got to be what? A real number. That makes sense? Everybody okay? Yes, no? And they're all basically the same. Source A and B. Source A and B can both be tagged. Source, either one of them could use immediate addresses, but they don't. I'm not sure it would give you an error, but it wouldn't make any sense, right? You understand? To add 5 plus 5 and use immediate addresses. Multiply. So here they changed over to real numbers. So here, because they're dealing with what? They're dealing with fractions. Notice they're all using tags. So you can change that over. By default, it's going to do it again, right? You understand that? So if you know you're going to be dealing with fractions, then you have to go into the tag table and change it over to a real number. Divide. Here they're using dents, so that means they're not anticipating any fraction. By the way, I think I don't think it'll give an error. We might try this. And I think it'll just choke you. I think it'll just go on the fraction portion of that. If I remember. The compute instruction. Now this is the guy that is really, really, really neat. And I forgot to get the order, but it's basically the order that you want to. What you do is you just put your equation into the box. So this one, they're taking the value of this tag and multiplying it by 5. So this is an answer by what you multiply. Then they're taking this value, so it's 57 divided by 7. And they're going to divide it. So this is a really powerful instruction because you can do what? Instead of taking this answer of this one and then divide and take the answer of that and multiply and take the answer of that and having a lot of math instructions, you can just come into here and do what? Put your formula in there.
Too bad I don't have any more math classes.
Huh?
Too bad I don't have any more math classes.
But you know this, right? So you did learn this math, right? So all we're doing here, this is a we're not going to do that in this class. God wants you to know that this instruction is loaded. So what I say, if I add two numbers together, and then I turn around and take that answer and multiply it by something, and I turn around and take that answer and divide it by something, that's going to be 3 rungs with a bunch of instructions, right? You understand? When I could have done it what? With one instruction. So the compute allows us to do what? It allows us to put our formula, standard formatting here. Except here, these are tags, these are not numbers. So, actual numbers, so they would have to pull these from these two locations. These are the other ones. We don't teach trig in here. If you take AC, you'll learn trig. We can take the sign of a number. We can take the SOHCAHTOA. This is when you're dealing with angles. This would work a lot when we're dealing with like milling machines and stuff like that, or maybe, a programmable welding machine. Sine, cosine, tangent, and then this would be the angle. So sine might be, 0.707. And then when you took the cosine of that, and you took the arc sine of that, 0.707, it would come up to say 45. So the arc sine gives you the degree that has that tangent, that sine, and then the sine gives you the sine of the degree. Luckily, when I first took trig, we had tables instead of doing the math. We had tables that we'd look at, but now we got calculators that do this for us. By the way, most calculators call this like the tangent minus 1, which is the same thing as the arctangent. So on your calculator, it's got tangent minus 1, sine minus 1, cosine minus 1, and tangent minus 1. That's the same as taking the fraction and getting the angle that represents that fraction. And these are all just
these are all just ratios, guys. So these deal with right triangles. And this is the angle that we're interested in. What do we call this side of the triangle? The hypotenuse. And then over here, since this is the adjacent to the angle, and this would be the opposite. And then we say Oscar had a heap of apples. Sally could tell. So only, this is right angle trig, and all it deals is the right triangle. So the sine is the ratio of the opposite over the hypotenuse. The cosine is the ratio of the adjacent to the hypotenuse. And then the tangent is the ratio between the opposite and the adjacent. And you wouldn't believe what we could do with this to deal with angles and shapes. Anybody take trig in high school? Yeah, so what you do is you'll take like these triangles and you'll break it into right triangles, and then you use these formulas, and then you add them together. It's really neat. So just about any triangle, you can any shaped triangle, you can split it up and turn it into right triangles, and then you use that to solve for everything. So it's really neat. Of course, we use this. Where are you going to get into this at? AC, yeah. Because AC is developed by this. Of course, then we have logarithms. We have natural log. Natural logs are weird together. Then we have common log. And then we have this that allows us to do what? Raise the power. So these are other math equations that we have. To take table slices in insulation, we're talking about logs. Even when you get into some of these classes, when they start talking about decibels, have you ever heard of dB? Decibels, dB. If you're in audio, you're going to hear about dB. Or if you're into any type of communication system, you're going to hear about dB. Basically, a log. So the log, the common log of 100 is 2 to the 10. So all the log is that guy right there is what 10 would be raised to represent a number. That's all the common log is. And then we take that common log and we multiply it by 10 and we call that a decibel. So 10 to the second would actually equal to 10 dB. So now you know. So a lot of people get scared of logs, but logarithms are just ways to represent very large or very small numbers with fewer digits. And that's exactly what we do. dB, what you do is it gives you the ability to round. So any number can be represented in a log. Common logs are what 2.73 would be raised to. So there's things that deal with things that vary like this, varies in the slope. Oh, clear? So we could use this instruction. Remember when we use the reset on the counter, it counts it skips over 0. Did y'all notice that? So when we hit the reset on the counter, you hit it, if you use the count, if you use that to use a switch to reset, if you use the same switch, it'll do what? It'll count 1 and we miss 0. So we can use clear. So what does clear do for us? We can clear any memory space we want to, right? And it'll set everything to what? 0. What does negate do? Change the sign of the number. So what we do here is we don't lose the original number. This is the original number. This will be the sign. So I'll take a positive number and make it negative, and then take a negative number and make it what? Positive. COD. This is when we start dealing with displays like HMI panels and stuff like that. And we want to display numbers on an HMI panel. Well, if I was to send the number out of my PLC over there, it would be binary. You wouldn't understand it, right? You understand that? So this is a method we can use to do what? Convert a what? Okay, remember, even though the PLC programming application displays decimals numbers, the numbers are actually binary. The TOD instruction converts a binary number from on the source to a BCD number and places it in that. This would allow us to take input from this tape, BCD, converts it into what? This thing. This will take BCD and convert it into binary. So this would be like we were bringing information from the thumb wheel switches. You know what thumb wheel switches are? You ever seen them? Usually they go from 0 to 9, and what they do is they put out a BCD number. This would allow us to take information from one of those devices and convert it into binary to use inside our PLC program. Yeah, that's it. Anybody got any questions on add, subtract, multiply, divide? Everybody okay on how to switch what number system? So what does it use? What does it use by default on all our math? Yeah, it uses a dent, right? So if you're going to use any fractions in any of your math, then you need to go into the what? You need to assign tags to everything. And you need to do what? You need to go into the tag table and hit edit and then change the number system and change it on which side, what are you using. And we'll see this. We'll play around with this a little bit when we get into our logic, which is in our next lecture. I think the next lecture would be, of course, we have a test if we get these computers working. And I think we're okay. I mean, connect up to somebody else's PLC and see if you can get it that. So, well, you know, being able to communicate with a PLC is nice having your own one there, but it doesn't mean that we can't do that we can't share, right? We can write our programs and share. All we got to do is make sure that whichever operating system you have, when you set up the program, you got to have at least one version. Run on these PLCs. Version what? 32. Y'all know where you see that, right? So what's happened, and this was, I'm not going to record this. This was my fault.